Hello, everybody. That was nice. Everyone's head went up in unison. Very nice. Welcome. Got some more Zoomers joining us. Let me welcome them as well. There we go. There, everybody's with us. So, how is homework going, folks? A laugh. That can't be a good sign. Would anyone like
I'll
to?
See you in office hours.
You'll see me in office hours. I will see you there. Yes, office hours today from 3:15 to 4:30 as usual. Any questions that you'd like to take this chance to ask now? I'm always going to offer, but you don't have to take me up on it. No. All right, then in terms of looking, yeah, go ahead.
Okay, I had Cassie explain effect size twice yesterday. Could you do it again, please?
An effect size is a measure of association that is in a metric that we know what to do with it. It's intuitive. The ones that you know so far are R, and I've mentioned it briefly, D, which we'll come back to later in this lecture. R is a correlation effect size. So it goes from -1 to 1, where 0 means there's none. We take our effect sizes, convert them into a test statistic as a function of the number of people in the sample, and that's how we decide whether or not that effect is significantly different than 0, is sufficiently unexpected to have happened if there were no association in the population. Okay, does that help? Yes?
Thinking of it as correlation effect size.
Yes, a correlation is it's more generically it's R, but the label that you can put on it to keep it from floating away in your head is correlation. Like there's the Pearson correlation, there's Spearman, and there's literally a dozen other kinds that differ in how they're calculated or estimated. But the metric that they're in, that R metric, is the thing that's its effect size. It has nothing to do with sample size. It's like the R is the R. Whether or not that R is noteworthy is a function of sample size. Okay. Other questions? All right, then just a little bit ago, I put up your next formative assessment, number 3. If you could get that done by Wednesday night, please, we can go over it the Thursday before spring break. Woo! Spring break, Iowa. Gonna catch up on laundry and work. Anyone doing anything better than that? No? You're going to Tejas? Is that for fun?
For a conference.
For a conference. Okay, well, have some fun while you're there at least.
I will try.
Okay.
Not get sick either.
Yeah, no one gets sick. That's the other fun part here. Could be worse. My sister-in-law just went back to work in California. She's an ER nurse after maternity leave, and it was her hospital where the coronavirus person was who got off the cruise ship. So yeah, welcome back to work after your maternity leave, because there's no one in her house that we would be concerned about being immunocompromised. So it could be worse, right? We're all relatively safe and healthy here, I guess. So yeah, on that cheery note, how about we talk about what we came here for? What do you guys remember from last time? So. Linear models, yes. As usual, I will take words, phrases, gestures, grimaces also. I'll put in there with gestures. What do I mean by linear model? Do you remember that part? You're allowed to phone a friend if you want. If you want to throw the question to someone else, that's okay too. Papa Boone. Linear.
Linear.
Yes, linear is linear, yes. So that's the particular type of relationship that we started talking about is linear, but linear model is a more general term.
Wait, so linear, you weren't just being cute, like that's actually the way people...
Linear is based on the word line.
Right.
I don't know that anyone besides me would pronounce it that way,
Okay.
but I was
So,
trying to
like,
make a
if I
point.
show up at, like, some kind of professional situation, people say linear.
I wouldn't recommend it.
Okay.
Not unless you're going for laughs or irony or something like that. But yeah, linear is linear, right? I was trying to make that association. But linear model is a more general term. It's the form that the model takes in predicting an outcome is a constant times a variable plus a constant times a variable. So the particular kind of variable that we started putting in the linear model is a linear effect of a quantitative predictor. So that's a more specific instance. Okay. So how about terminology? Do you remember any new letters? Beta. Yeah, the B looking thing.
Beta 0, beta 1, beta 2.
Beta 0, beta 1, beta 2. So let's start with beta 0. That's our new friend, the intercept. So for instance, this is slide 6. Your very first linear model, oh, that was slide 6, is right here. So y sub I, what's that again? Individual outcome column, so that's an observed variable that's sitting in your data set, is a function of beta 0. Beta 0 is always our intercept. The definition of that is it's what y is expected to be if all the predictors in the model were 0. Right now, we have no predictors. So beta 0 takes on our best naive guess for what y would be for any person, which is going to be, feel free to read it from the slide, the mean, yeah. If we don't know anything else, we guess the middle value. That's what this model is going to give back to us. The other thing that it's going to give back to us is an E for each person. E is a residual. It's how far off from what is predicted your actual outcome is. We don't care about what E is for each person. What we care about is the variance across people in the E's, and we want to watch it go down as we refine our prediction by adding additional information to predict the outcome in the model. So that would be, for instance, beta 1. Like this one right here. Beta 1 is a slope. It's the difference in y per unit difference in x. And this is where the term linear starts to show up. If x is a quantitative variable, then beta 1 is a linear slope. No matter where we are on x, if we increase 1 unit in x, y goes up by beta 1. That's its definition. Beta 1 is because this is the first slope. If I had another x variable, then its fixed effect would be, what comes after 1? 2, very good. And the next one? 3. Yeah, this is the subscripts here are in indices. It's just keeping track of the betas in order. And they don't have i's. Why not? They're what?
Not the individual scores.
They're not individual terms. They are constants. Everybody shares it. So in predicting each person's outcome, people share the intercept beta 0. They share the fixed slope beta 1. X, however, is another column in your data set that each person has one of, and that's why it gets an I. Likewise, if we predict what y should be using x, E is how far off you still are from the y that's actually in your output, or your data set. So E is individual specific, and that's why it gets an I. So then the I's and the lack of I's can help you try to figure out what these things actually mean in a given model. Beta 0 and beta 1 are unstandardized. When they come out in your output, they will be unstandardized. What that means is they are scale specific. So for instance, we started looking at, let me skip some of this stuff, education as a predictor of family income. So that's education in years, family income in thousands of dollars. And so the numbers here reflect that scaling. The solution on the right, this is slide 11. I fed the example data that we're going to play with in a moment into SAS, and it spit back these numbers for me. So y with a triangle looking thing over it, what's that called? Y hat, what's it mean? Oh, I forgot the theta hat again. I heard lots of muttering, but no definitive answers. I once had a professor tell me it's better to be wrong than vague. So be loud and wrong if that's what you are. What's theta hat tell us? It's per person, right? We know that much because it has an I. What's missing from this line here that's in the first line?
It needs to be fixed and we need to not have a negative. Negative 51 is a problem.
Negative 51 is a problem. It's not wrong, but it is weird.
But I don't know if that has anything to do with why that.
It does not.
Okay, it's irrelevant.
So the difference between these two lines,
Doesn't have the error.
yeah, the bottom one doesn't have the error. So another way of saying that is y hat is what is predicted by the model to be your outcome. So anybody with the same level of education has the same predicted outcome, has the same y hat. What your actual outcome is the difference between what is predicted for you and what you actually got. That the difference is picked up by E. Remember, E is a residual. It's error, although I don't like that version. Offness, deviation. It's a discrepancy, generally speaking. So yes, according to this model, the slope drawn through education results in these predicted incomes. It's not perfect. Each of these observed points has some distance from the line. That distance would be each case's E. Now let's talk about this negative 52. Jen doesn't like this, right? Why don't you like this, Jen? Because I agree with you.
When I do my taxes, that's what I have to report,
That you made negative $52,000?
basically.
Fair
That's why I don't like it personal.
enough, yes.
I don't know why.
Schedule
have a negative
Schedule C income.
Unless you do.
Yeah, if you take away if you don't make very much money and you deduct your business expenses, then you can end up with negative income on your tax forms. But more generally, can I make negative $52,000? Did anyone in this sample make negative $52,000? No. So it's weird, right? Negative income is just a weird thing. But is it wrong?
Context will tell you.
The context will tell you it's technically not wrong because it is the logical result of following this slope all the way down to this point right here.
But it's not the most efficient way for us to be looking at our data.
It's not the most, I would say, intuitive or useful.
Useful.
Yeah, mathematically, math don't care. But in terms of us making sense of what these numbers mean and being able to use them, then we care. So the intercept is the expected outcome when all your predictors are zero. In this context, the intercept of negative $52,000 is the predicted family income for somebody who's never been to school. Education equals 0 years. That person doesn't exist in our sample or likely in any sample where someone had to be able to participate in a survey. So we can fix it. Do you remember how we fix it?
Standardized.
That's one way we could fix it. So the solution on the left is one way to fix it. That is, well, let's just remove the scaling of the variables altogether. Let's not talk about years and dollars. Let's just put it into a metric that each variable is on the same scale, such as a z-score, where each variable has a mean of 0 and a standard deviation of 1. Then the intercept is right here in the middle of the data, mean of 0, right here. It's the same degree of relationship, but it's now on a different scale. So this 0.45, that is a standardized slope. You will see that in your output. In this case, where it's just one x predicting one y and they're both quantitative variables, what is that number? You've seen it before. Standardized slope is the same thing as Pearson effect size. Yep, this is a Pearson correlation. That is what a Pearson correlation means. That as x goes up by 1, y is predicted to go up by 0.45. So what is the highest my standardized slope could be? 1. Yeah, that would be a perfect relationship, right? What would be a perfect relationship in the opposite direction? -1. So yeah, standardized slopes are bounded between -1 and 1. Is a slope of -1 smaller than a slope of 1 in terms of effect size? No, they're the same. It's just a different pattern. How would this graph change if this standardized slope were negative? Yeah, gestures please. Yeah, this way. Negative slope. As money goes up, income goes down. So that's one way we can fix it, to make this -52 less than satisfactory. But what if we wanted to retain our original scaling of years of education predicts this many dollars? How else can we fix it? Centering, yeah. What's centering?
You take the plate, put it on the wheel,
You do what?
and then you breathe out. In ceramics,
Yeah.
In ceramics,
I'm with you.
I'm with you.
okay, I'm gonna need some explanation here. I don't do ceramics. You do what with a plate and a wheel?
You have to like throw the blob of clay on the wheel.
Okay.
And
The
it's
wheel's the
spinning
thing
in a
that
circle,
spins
but
us.
the clay's not in the center.
So it
So then you
wobbles.
have to like squeeze it into the center,
One on
in
top
and
and one on
down.
the side.
That's called center.
Okay.
Multiply that constant?
Not multiply, very close though. Yeah, it's the same concept. It really is, because you're taking the predictor and you're trying to shove it
Right.
like 0 towards the middle of it. But the shoving is a lot easier than clay, because adding or subtracting, yeah. So what you're trying to do is make 0 in the middle somewhere. It can be exactly in the middle, like a mean, or it can be close to the middle. There is no wrong place to center. It's just you want to pick something that has a reference point. Question?
Dumb question.
I love dumb questions.
Okay, well, it's, I think, an optical illusion, because I would assume that those lines have the same angle, but from here, it looks like there's different angles.
They're on different scales for what the x and y axis
Yeah,
is.
so it's optical.
So it's the same strength of relationship, but it's like in units of what per what are different, and so it's not the same. So it'd be like if you converted from inches to centimeters or something like that. Like the numerical scales are different, the information
Yeah,
is
but
still
the
the same.
angle of the angle should be the same, right?
Not necessarily, because yeah, like this is ranging from a positive z-score of 2 to a negative z-score of 1, whereas this axis I actually extended so that I could show the minus 60 on it. So this extends further south, if you can, further into negative territory, so it's not going to be exactly the same. It's the same information on different scales, is what I can say. But yeah, here's how we can fix it. We're going to center this thingy. So we talked about Atlanta's airport. We need the UR here sign. So we want the fixed intercept, my beta 0 here, to be a useful UR here sign. A useful reference point for how you talk about changes in x relative to that for the rest of the model. So in this case, let me see here, these lines should be on the same scale. So the y-axis goes from negative 100 up to 200. The x-axis goes from almost 0, no, not quite. This goes a little bit further. So these are very closer to the same scale, but not quite. But the big difference is this number right here. This one, 27. So the slope is the same. If I use original education, in which 0 is 0, I get the same change in y per unit change in x, change in income per year of education, as if I take education and put in minus 12 instead. So I haven't in any way cheated or distorted the information. I've simply moved the intercept over to a place that can possibly exist. So now my reference point is somebody who has a high school degree. In this data set, they are predicted to make about $27,000. For every year past high school, this line suggests that you're going to make another $6,600. So this is the best guess according to the model. More specifically, the way that it came up with these numbers is as the numbers that make this set of e's the smallest they can possibly be. So we're trying to make what's known as the sum of squared residuals, the numerator of the variance term, that thing as small as possible. And the math works out that to make the variance of these e's as small as possible, we need these two numbers. There are straightforward ways of figuring this out only in limited cases. That's not something that I'm interested in having you spend a lot of time on, because the program will do the math for you. And you can't even do hand calculations once you get past fairly simple examples. But yeah, the point of centering is to make the intercept more interpretable. That's the point so far. Okay. How are we doing so far? Tentative nods? Either that or post a lunch caffeine slump? Cheers. You're okay? All right. So then we talked about residuals, right? Residual is how far off from the regression line you are. So we talked about this person here who makes $155,000 a year, in part because they went to 20th grade. Education, where 0 is 12, is 8 for this person. Now, why do I say in part because they went to 20th grade and not because they went to 20th grade?
Because all that stuff on the top.
All the
blue
stuff
line,
on the top,
The blue line.
the blue line.
We don't know.
Mhm.
It's also important in understanding why they make that much money.
Exactly. The line suggests they should make this much money. They're supposed to make about $80,000 from having gone to 20th grade. They make almost double that. So adding education in as a predictor helped make a better predicted income for not only this person, but everyone else, but it's not the whole story. Otherwise, all of these points would fall right on this line. They don't. So there's other stuff that's out there that we would want to try and take into account. Whether or not this is a useful line, whether or not it's sufficiently not flat, is partially indicated by how much the variability went down of the e's. So in my empty model up here, if I make the same prediction for everybody, everybody has a predicted income of $40,000 because that's the mean of this variable. 1980 is the set of offnesses, how far off each observation is, y sub I, from the one that's predicted by the model, which is the 40 for everybody, squared, added up, divided by n minus 1. So this is as much variance in income there is up for grabs. After we put in education, because of this slope of 6.6, it works out now that the difference between each person's income and the income predicted by education, squared, sum it up, divide by n minus 2, 2 because now there's 2 betas here instead of 1, it goes down to 1594. So we're going to look at two things in terms of how we think about slopes and their utility. One of them is how much variance did the slope reduce? How much do we know now that we didn't know before in terms of the potential reasons for differences in income? The other is just, is this slope significant? Meaning, if the real association in the population were 0, what are the odds we'd find this? Is it expected or unexpected? And you guys already know how to do that part. Right?
Yes.
Yeah, you do. Do-do-do. Thank you, Sophos, for updating my virus protection during class. I appreciate that. Updates will complete when you restart. Okay, well, at least it's asking me if I want to restart. That's nice. So here's what we're going to see in terms of information about our slopes. Estimate, that's the slope number itself, like the 6.6. It's going to have a standard error. Just like we had a standard error of the mean, and you could have a standard error of a proportion, or a standard error of a correlation, we're going to have a standard error of a slope. That tells us how far off our slope is in the sample from the expected mean slope in the population. It's an index of imprecision in that smaller numbers are better. That estimate divided by the standard error is going to be our friend t. Remember our friend t? Distribution? Yeah. T helps us locate where our slope is relative to a population slope of 0. So it's going to give us a test statistic that tells us how far unexpected our slope is. And we're going to be looking to see whether or not it crosses that expected unexpected line. That line is determined by our alpha. Remember what alpha is? Lot of vocabulary today. Alpha is a Greek letter. It is what in this context? A synonym for alpha I gave is aberrant.
Aberrant. Oh, the threshold for aberrant.
Yeah, this thing. It's the, here, I'm going to get out paint rather than, yeah. Go ahead. Unexpected, yeah. So here's my best rendition of a t-distribution. There's 0. Okay. Alpha is our a priori determination of where we're going to distinguish expected from unexpected, and it's based on probability. What is that line is supposed to be flat? Let me try again. See, not only have I not done pottery or painting, I can't even draw in paint. But I'm going to make it work. So we're going to put some sort of cutoff here and here. What is it called that I'm going to have a cutoff of both too high or too low? Two-tailed. Yes. What does it mean to have one-tailed? Yeah, one or the other. One direction is generally voodoo. It means you're stacking the deck. There are very few instances in which one side or the other would not be meaningful. What we're looking for is the combined area right here and right here that takes up what percentage of the observations? What's the magical alpha level that everyone in the social sciences has decided on? 0.05. Is that arbitrary? Yes, but we've all agreed on it. So if I select an alpha of 0.05, that means that this area right here and that area right here sum to 5%. Everything in the middle here, I'm going to try to write with my mouse here. This is expected. 95%. And then this is 5%. How do we know what that line should be and that line? Where do those come from? Correct. They come from the computer. They come from the critical values for your t-distribution for the degrees of freedom that you have. Rather than look it up on a table, the computer has that information locked in. And rather than simply telling you what your critical value is, it will tell you what your actual t is. Numbers that you can commonly refer to, a t of, that's a 2, plus 2, or minus 2. Yeah, roughly 2 standard deviations. Those numbers wiggle a bit, particularly in smaller samples. They'll be bigger, but they'll never be smaller than 2 if you're talking about a 95% confidence interval. So if I took, let's say that I had my slope, I'm going to round, it's 6. And let's say that my standard error is 2. That means my t-value is 3. That'd be like out here. So what does it mean to have a t out here? I'm right here. I'm drawing a happy face next to my t. It's unexpected, meaning that if the true slope were 0, we would see a slope of 6 with a standard error of 2 that gives us a 3 on this distribution, less than 5% of the time. And the program, in addition to telling you that the t is 3, will tell you the exact probability. It would give you the exact area under which you would see a result more positive than that t or more negative than negative 3. What if I had a slope of 6 and I had a standard error of 6? Now I have a t of 1. That's like right in here. So I'm drawing a sad face for that t of 1 because it's expected. It looks like it was something, but really there's so much noise around it, it's not noteworthy. So synonyms for within expected, non-significant. How about the null hypothesis? How would we phrase it relative to that? Retain. Retain or do not reject. Meaning we don't have enough evidence to say that it is unexpected relative to 0.
Why is it sad?
Why is it sad?
It wasn't expected, but.
Well, because I expected it, otherwise I wouldn't have collected these data and analyzed them. So that brings up a good point. The null hypothesis in looking at associations is almost always a zero association. And so you can say that relative to no association, what I found is expected or unexpected. But there's no requirement that it goes that way. You are allowed to have a null hypothesis that is not zero. It is called a non-nil null. I swear to God, that is what it's called. I'm not being funny. A non-nil null. So if, say, in previous research, you had found a slope in comparable scaling of 2, right? You could compare your 6 to a 2 instead. There's nothing stopping you from that. You'd have to tell the software what you were trying to do and have it figure it out. But the missing part of this equation right here, it's the estimate minus what is expected by the null. So what I'm doing right here is this implicit minus 0 for what it was expected to be. You could put a 2 there instead. Nothing stopping you. And the reason this would be a sad face is if I were trying to show an association between these two variables, the conclusion I would draw is that they're not associated. I don't have enough evidence to say they're associated, which is a bummer, because I went to all this trouble to go and find an association. All right. Now, what if reviewer 3 comes back and says, but 6, how do you know if 6 is a lot? It might be significant, but is that good? I don't know. Then we need an effect size. There's a lot of different ways of assessing effect size in linear models. The easiest one would be to convert this 6 into a standardized slope. If you only have one predictor, then the standardized slope is the Pearson correlation. So in the example that we're playing with, the Pearson correlation was 0.45 between these variables, which translated into an unstandardized slope of 6.6. Okay. All right, so this process of taking a t-value, figuring out the corresponding p-value, and deciding whether or not you're going to reject the null hypothesis, this is known as a univariate Wald test. This is something that will show up in many, many areas of statistics, the same idea of estimate divided by standard error as some sort of test statistic. It will almost always be a t. It will switch to z in instances in which you don't have denominator degrees of freedom. Either you are using software that doesn't use them, or you have generalized models for not normal outcomes. That's the next class, but it'll be t from now on in the rest of this class if we're testing one slope. Okay. The standard error for these things. This is slide 17, picking up on a little bit new information. Here's the formula for how a standard error is made if you only have one slope. It's exactly the same idea as a standard error for the mean, with one new ingredient. So standard error is square root, so all the things in here are on variance metric, squared metric, residual variance for y. So when it was just the standard error of the mean, this number would have been just the variance of y. Now it's y variance left over after putting the predictor or predictors in the model. So that's our friend sigma squared e, the variance of the errors specifically, of the residuals. We still have a function of sample size in here. Now it's, instead of n, it's n minus k. K is the number of betas, the number of fixed effects. It's the number of quantities that you had to estimate in order to get your residual variance down to this. It's 2 here because I have an intercept and a slope for education. That's 2. If I added a second predictor, it'd be n minus 3 instead of n minus 2. And last but not least, because the slope is in units of y per units of x, we got to adjust for what x is. So units of y is adjusted by the numerator. Variance of y for units is in the denominator. So the same rules that guided the standard error of the mean are at play here. Your standard error is going to be smaller whenever there's less variance left over, That's the sigma squared E is smaller. Or you have more people, bigger N. So if I put those numbers into the formula here, and am I ever going to make you guys do this? No. Why am I showing this to you? So that you know what the math is doing in the programs. The standard error works out to be 1.35. So 6.6 is my estimate for my slope. 1.35 is an estimate of its imprecision, its wiggliness. That gives me 6.6 divided by 1.35, a t of 4.9. Let's go back to my happy little picture here. It would be, come on, Mr. Mouse, come back. Here we go. Somewhere out here. 4 and some change. So we're well in unexpected territory. The exact probability of getting a t of 4.9, if the null hypothesis were true, in this case meaning that we have a expected slope of 0, would happen less than 0.01% of the time. So even if we had adopted a more stringent alpha, if we had said, well, 0.01 instead of 0.05, or 0.001, this would still be declared unexpected. So in interpreting Pearson's correlation, you guys are getting practice with this in your homework. A positive correlation means as x goes up, y goes up. A negative correlation means as x goes up, y goes down. So the same principle here. It's not enough to say our slope is significant, the end. We got to tell them which direction it's going. So I would say predicted family income, meaning the y, is significantly higher by $6,600 for each additional year of education. So there are only 4 possibilities for what would go in this bold section right here. And you will see this repeatedly in your homework. You can have significantly higher, non-significantly higher, significantly lower, and non-significantly lower. How would I delineate which is which? No, I'm going to tell you, because there's an easy formula for it. I swear. So number 1, is your slope a positive number or a negative number? If it's a positive number, higher. If it's a negative number, lower. Next one. Is your t significant? Meaning, is this p-value that goes with it less than alpha, which is always going to be 0.05 in this class? If it's significant, then I would say significantly, and then whichever direction the slope gave us. Now, one nice thing about t is that it is also signed, meaning t can be positive or t can be negative. So technically speaking, you don't have to look at anything besides t. If this slope were negative 6.6, I'd have a negative number right there. That would result in a negative t, significantly lower in that case. Let me go back. Yep. Let's see. Yeah, let's just do one more thing, and then I'll show you how it works. So this is a standard error of a slope. It's a way that helps us determine how unexpected the slope is relative to a no slope, null hypothesis, and given our sample size. Standard errors for predicted outcomes are a little bit different. I need a gimmick for this. I got one of these a long time ago. Teacher pointing stick. Yeah, nothing makes you feel professorial when you're like 29 years old and everyone looks the same as you as a big stick. So I speak softly and I carry a collapsible stick. So it's also helpful for poking people if they fall asleep. But
I have one with a little claw and string.
there you go. You could loan it out for people. But yeah, I got to use my stick so. So my positive slope, let me go back to my picture here. This picture, positive slope. I have my stick. Sorry, Zoomers, I'm holding a stick. It looks like a radio antenna. if the slope changes, look at where my fist is in the middle. It doesn't move very much, right? Now, if I put my hand on the outer part and the slope changes, where my hand is moves a lot. I think there's a word called fulcrum that has something to do with this. Can someone help me?
Yeah.
Yeah?
Yeah.
That sounds good? Yeah. So the same logic in terms of trying to predict what your y outcome would be on the slope. The outcomes that are in the middle of the slope wiggle less. They have more precision to them because they would stay pretty much the same if the slope changes, whereas the ones on the outside are going to swing more. So that creates a confidence band around this predicted line that has some swing to it. The formula to put it on there looks like this. The extra part is that it wants to know how far away from the mean on X you are. And I have a picture of how the software generated a confidence band for me. This is slide 19. Do you see the blue shading? That's the band that describes the 95% interval of what the predicted y outcomes would be from this regression line. So it necessarily gets wider as you move away from the middle, where there's less precision. The dotted lines, the blue dotted lines, that also takes into account the amount of error that we have in the model, the amount of residual variance. And so this is a window around the predicted observations, the predicted y's. So the blue shaded part is the y hat prediction. The blue lines is the overall y. And so you can see that that's humongous because there's a whole lot of error variability in this model. So this matters if you are using these sorts of models for actual prediction. So that happens in industrial organizational settings like human resources, where you might give a bunch of applicants a test and try to predict how well they're going to do on some job performance measure. Your predictions are going to be more noisy the further away from the mean you are on the predictors. So that's just something to keep in mind. In practice, your software will give you all of these predictions and the standard errors that go with them. You don't have to know how to get that all by yourself. And it will do it no matter how complicated your model gets, which is very helpful. Okay, how are we doing? Okay, we're all talking about pottery and physics and, poking people who fall asleep. I once went to, when I was a postdoc, I got a chance to tag along with my postdoc mentor to Europe. I got to teach in part of his workshop, and I gave a talk at a university in Switzerland, and they had a stick that, I'm not exaggerating, it had to have been 8 feet long and weighed like 20 pounds. It was wood. And so I remember trying to pick it up and gesture with it like I was lifting weights or something. I have a picture of me trying to hold the stick up. It was my webpage profile for a while, but I had to eventually take it down because people are like, "You're not in your 20s anymore. You can't have that picture up."
Yes, you can.
Yes, you can. Yeah, if you want to laugh, by the way, go to the faculty websites on our college or any college and see how old the pictures are. There's going to be quite a few people who haven't posed for a new picture in years. I am also guilty of that. I took professional pictures when I had enough reasons to get one at Sears in 2008 or 9. And I have been using that picture ever since because I'm like, my hair magically goes back to its original color every 4 weeks or so. It's about the same length. I can make that work. So, anywho. Do you guys want to see how to make SAS and Stata do this cool shit for you? Yeah, why not? Okay, so I've got example 3. I have a lot of sort of preliminary stuff here that your homework starter files are already designed to have. So I'm trying to show you everything that the program would do, but you don't have to write all of this stuff. So we are using the same data set that I played with in example 2. It's a subset of the General Social Survey from 2012. It's the one that's in the Stata textbook that's in your suggested list. First step is always to tell the program where your stuff is. Where's my stuff? The way that I'm doing that in SAS is to define this placeholder variable, this abbreviation file save, with the path to where my stuff is. So you would change that to where your stuff is. Next, because SAS will import Stata data sets, but Stata will not import SAS data sets, at least in the older versions that I have across my computers, I went ahead and converted it to Stata to use, or took the Stata data set and just imported it into SAS, I should say. So I have example 3 is what this is going to be called. This ODS RTF, that's opening up a results file to send all of my output to. That way you don't have to save it yourself. Stata syntax do the exact same things. File save is here. Stata wants your path in quotes. Then you can tell it the name of the data set that you want to import, so example 3. And then the log statement starts a non-rich text file, just a plain text file to send your output to. Next up, data. First thing we have to do is make sure that we have all the right versions of the variables that we're going to play with. So this is where data transformations need to happen. Yeah, in SAS, this line right here goes first always. This tells it which data set to read in and add stuff to, and what to call the new version that has the added stuff. So data work.example3 means make me a new data set, put it in this work temporary directory, call it example3. Set means from the data set in the work directory called example3. In other words, save as itself. Go into the data, make me some new stuff, and save it back to where it came from. Stata people don't have to do this. There is no analog. In making a new variable, we're going to predict family income in thousands. So the format of this, FAMINC 1000, that is a new column. I'm telling it to name that new column that word. And what do I want to go in the column? My original variable that's already in the data set called FAMINC divided by 1000. So it's always new equals old. And this is a linear transformation of the outcome. I did that to keep the values in the scale, the slopes from going crazy. Here's another example of a linear transformation, making education. So again, new equals old. My habit in making centered variables like this, in making a new version of a predictor in which a constant is added or subtracted, is to put the constant as part of the new name. So EDUC, education 12, is my way of saying education centered at 12. That way I don't have to remember what constant I picked. It's going to be the original education variable minus 12. And then I'm adding a label to the new version. That way I know how I made it for my own future reference. One more. This is making a variable that is literally a copy of an old one. And you can thank last semester's class of 6242 for me introducing this extra step, because the original variable is a binary variable called married, where 0 means unmarried and 1 means married. It got really confusing to keep track of when the variable married was being used in the code versus the value of one of the categories that was also called married. So to avoid that problem, I am creating a new predictor that is called Mary group. Like, which group are you in? And it's just binary. We're going to see this one later next week. Last but not least, I wanted to show you how things turn out when they are z-scored instead, which is a standardized version of the model. So I am making a copy of the family income variable, putting a z on it, the education variable, putting a z on it, to then use it to make z-score versions later on. I don't think that, yeah, that syntax didn't get put in here, unfortunately. I'll have to fix that. It's in the one online, though. And last but not least, I am removing any cases from the data set who don't have all 3 variables that I'm going to use in this example. This is an example of a function. So the functions that are built in to SAS and Stata are very useful for lots of things. This function is called nmiss. What it does is return the number of missing values across the columns that you specify in parentheses as the arguments to the function. So in English, this says, if the number of missing values for this person's row of family, income, education, and married is greater than 0, then they're gone. Bye-bye. Then delete. Because I can't use them in my models if they don't have complete information. Okay. All right, SAS folks, questions on the setup so far? Not yet? Okay, you reserve the right to have questions in the future. Stata folks, very similar. A few small adjustments in making new variables. The pattern of making new variables is still new equals old, but you have to put the word gen in front so it understands what you're trying to do. And there are no semicolons in Stataland. It literally will yell at you. It doesn't know how to handle them. So I'm making fam inc 1000, a new variable from the original variable divided by 1000. Likewise, I'm making education 12 from the original variable minus 12. Married group is a copy of married. This is the z-scoring that happens within a data step in Stata. It uses an egen thing, and std is a function that is for standardizing. Z-score is the default of the function, I believe. And then last but not least, this part. It's an analog to the nmiss function in SAS. It's called rowmiss. It's creating a new variable called nmiss that holds the number of missing values, and then telling it to delete those rows if the number of missing is greater than 0. You guys are not going to have to worry about missing values, okay? I promise. I'm not going to add that additional layer of complexity. I just want you to know how to deal with them if you're out in the world. Solutions to what happens if you have missing information is a whole nother class. Classes on missing data handling. I get into pieces of that in my advanced classes, but for now, the easiest solution is just to drop them ahead of time because they're going to get dropped anyway as you add the predictors that have missing information or the outcomes to the different models. Okay. Questions on the data set up from Stata folks? Okay. So first off, more stuff you already know how to do. I wanted to give you some descriptive information about the variables we're going to be playing with. So for quantitative variables, which is what we're talking about thus far, I'm asking for SAS proc means. So this is relevant whenever you want to have estimates of central tendency, dispersion, and so forth. So all the stuff I'm asking for is right here. N means number of values, mean, standard deviation, variance, min and max, and I say variance because this var right here is not the same as this var right here. The latter means what?
Variable.
Variable. Meaning this is where you list the columns that you want information about. Var in the context above means variance. Analogously, in Stata is the summarize command that gives you quantitative descriptives. I had asked it to only print the values to 3 decimal places here, and this format statement in Stata does the same thing. So I just was trying to go for comparability across the programs. So here's what we have. 2 versions of family income that we're playing with today. So family income in thousands, the 39.7, that's the 40 that we were talking about earlier as our average income for the sample. 1980, that's the variance in income from the sample. So that's just the mean, variance, central tendency, dispersion of that quantitative variable. The one underneath it, a mean of 0 and a variance of 1. That's the z-scored version. So we're going to use that to get standardized effects. Likewise, education versus education z-score. Education has a mean of 13.9 and a variance of 9. Education Z has a mean of 0 and a variance of 1. Third version of education, education minus 12. So the means 13.8, 1.8 are off by exactly 12, as expected. Standard deviation? Same. Variance?
Stays the
Same. Yeah. So, in other words, I've just took the whole thing and shifted it. I haven't stretched it or otherwise distorted it. It's just centered, exactly. Centered so that 0 means 12 years. And this, although it seems sort of odd, married group, I guess it would say. Yeah, it should say married group. Excuse me, let me fix that real quick. That's the old version, married group. This is a binary variable. 0 means unmarried and 1 means married. So what does a mean of 0.53 mean in this context?
It's about half and half in each group.
About half and half. This is a proportion. So the proportion of answers that are 1, meaning they're married, is 0.531. 1 minus that proportion gives you the number, the proportion of people who are unmarried. So it is about half and half. Here's proc univariate to make some pictures. So I want to call attention to this picture here on the left. How would you characterize this distribution? Positive skew, meaning that there's more people on the right-hand side. So it's asymmetric. How about these guys out here? Yeah. It turns out that this variable was truncated in the data set. If anyone made more than a certain amount, they just cut it off. So these are all the people who made some amount more and we don't know. Yeah. What if I told you that in order to use this model that we're going to use, family income has to be normal? Remember what normal means? Normal distribution? It's symmetric.
Right.
It goes on forever and ever in both directions. It certainly doesn't have a pile of people at 160. Yeah. It turns out that in order to use these models, it's not Y that has to be normal, it's E that has to be normal. So what's the difference? Y is the original outcome. E is the residuals of the outcome, meaning the discrepancies that remain after the model is done predicting the outcome. So we can't actually tell whether or not these models are appropriate from looking at this picture. I'll show you in a little bit how to look at pictures to try and make that decision. What to do instead is, again, in a whole nother sort of classes. But looking at the general shape of this can point you towards which type of regression family. The ones that we're talking about are for normal residuals, but there's other kinds that you can learn about later on, whether or not that's appropriate. So the way that I look at it, it's like, have you ever gone into a dressing room to try on something much more formal than what you're going to wear? Like you're shopping for a bridesmaid's dress or a prom dress or a tuxedo or a new suit, right? But you go in shopping and you have like gym socks on, you have like your bad bra, you know, your hair's up in it like a scrunchie, and you're trying to put on this thing and like, so what if I had the good bra and some heels and maybe some Spanx and better lighting? Like, could I make this work? Like you're trying to like forecast like what it would look like kind of thing. That's what you have to do in looking at these distributions. It's like, okay, this doesn't look great, but can I work with it? Is it possible that I could put in predictors that explain why these people are clear out here, and then their residuals would be with everybody else? So it's like, could it be normal by the time I'm making it work? That's the question. So it's not the marginal distribution, not the original. It's when we're done with it. But we don't know what it's going to look like until we're done with it. That's the catch. Education looks like this. Do I need to care one way or another what this distribution looks like for education? In this context, education is my predictor. We haven't talked about this yet. The answer is no. Predictors do not have distributions. Your predictor can be any shape, size, it can even be categories that aren't numbers. Anything goes. The only time we worry about distributions and assumptions of the model is on the outcome side, not the predictor side. Now this type of distribution, it looks quantitative. It also makes me look that maybe I might need to do something besides just put it in as one variable, because there seems to be like a hump of people here that have a high school degree. It might be possible, for instance, that's the slope regarding education. It would be different before a high school degree versus after. Just what I know about education and how it works. But that's for a later example. I'll show you how to fit those kinds of models. But for now, we're treating this as quantitative. Doesn't matter what shape it is. There's no assumptions whatsoever. Here's some more stuff you already know how to do. Let's get some correlations among these variables. So correlations among outcomes and predictors are of interest for sure. Also, correlations among predictors. When we get to the point where we have more than one of them in a model, we're going to want to know about that ahead of time too, to make sure that they're not redundant with each other.
Why did you use Fisher?
To get confidence intervals.
Okay.
This piece right here gives you the Fisher R to Z transformation by which you can get confidence intervals around your correlation. This CI2 thing in Stata does the same thing. So that generates this extra output right here. I didn't make you guys do anything with this because I wasn't for sure that I'd be able to get all of you to be able to install this extra piece to do it in Stata. But there's two things I want to show here. This is the correlation between education and income. Now note that this is centered education that's in here. So centered education is correlated with income in thousands, 0.45. That's the number we saw earlier. Would this number be any different if I put in uncentered education, the original one? If I put in original education instead of education minus 12, would that Pearson correlation effect size number right there be any different?
It was a linear transformation.
It was a linear transformation of education.
So no.
So no, that's correct. All I did was take my predictor and shove over the scale. It's a linear transformation, meaning the correlation with income would be exactly the same. So I'm not cheating or distorting anything by doing centering of my predictors. The correlation between income and Mary group is 0.3. So how do I interpret a correlation between a binary predictor and a quantitative outcome? So it's positive, right? We can agree on that. Right? 0.3 is a positive number?
Yes.
Okay. So we said earlier a positive correlation means as x goes up, y goes up. Yep. So as x goes up, what does that mean in this context?
Yes. You are married.
As you are married. So people who are married, that's the x going up. As your marriage goes up, then your income goes
up.
Up. Yeah. So it's weird to think about, but what it means is that people who are married are associated with having a higher income. If this were a negative relationship, then it would mean people who are unmarried are associated with having a higher income, or alternatively, people who are married are associated with having a lower income. You could say it either way. So yeah, we're going to see that play out in these sorts of models next time. This extra piece right here is to get confidence limits around the correlation. So that would be something else that you might want to report. This is our best guess using our sample data as to what the correlation is, but how noisy is it? Well, this is what we would see across replications of the same sampling procedure. Our correlation would be somewhere between 0.27 and 0.6, 95% of the time. So it's 0.45 sort of on average, and this is the limits around that. Okay, something new. Yay. SAS, ProcGLM, Stata, Regress. In ProcGLM, it wants to know what data set you're going to use, same as everything else. This extra command right here just makes it so that it doesn't truncate the labels when it prints stuff out. The second part, model, that corresponds to this right here. It's model y equals the x predictors, and the slash separates that from the options that follow. This right here is an empty model. So y equals, it looks like nothing. That's because ProcGLM puts in the fixed intercept, beta 0, by default. You don't have to ask for it, it's already there. Solution means give me what you think the fixed effects actually are, their standard errors, their t-tests, and their p-values. I would also like to have CL_parm, that's going to be my confidence intervals around these fixed effects, at an alpha of 0.05. So if I say alpha of 0.05, what confidence limits am I asking for? What's the opposite of 0.05? 95%. So if I wanted a 90% interval instead, what would I change? 0.1 for alpha. If I wanted a 99% confidence interval, then I want an alpha of just 0.1, yeah. So a 99% interval would mean 1% unexpected. That's alpha. Yep. And even though it seems redundant, certain procs in SAS want both run and quit to make it go.
Can you use stop?
I think that's for something else. Have you seen that one before?
I put it in and it didn't get mad at me.
Then you can use it. Yeah. Quit is for things where you have multiple possible iterations that you can do. It's like it closes the whole thing. This title, by the way, this goes with this right here. So what happens is when you put a title, those are words that echo to your output so that you know what you're looking at. Those words keep echoing over and over and over again as you run more stuff unless you shut it off. So the title that has nothing after it just turns off that line so it doesn't keep printing over and over and over again. Stata doesn't have that. Stata version of title is this display as result, and it prints this once and it decides it's done. Stata regress is even fewer words to type. You list the outcome variable first, followed by any predictor variables. There's none right here, so that's it. So the model that I'm fitting with this code is right here. This is an empty model. This is a model that has no predictors. It's our jumping off point for how we're going to predict income for each person. So far, our prediction comes from just one beta, one fixed effect, the intercept, which is going to be the mean. Because if you don't know anything else about a person, your best guess for their outcome is the sample mean. In terms of output, here's a whole lot of stuff. I'm going to let you skip all of it for right now, with the exception of this one number right here. That one number right there, it's under the mean square column and under the error row. That number right there is your residual variance. That is the variance of the E's after they are predicted by whatever betas you're using. If you don't have any predictors, that variance right there from the empty model is all the variance in income, and that's the exact same number that we saw earlier when we ran descriptives. The square root of 1980, by the way, is right here, 39, so that's our sample standard deviation. Under parameters, this is where your fixed effects are going to go. So the fixed intercept that it gave us without us having to ask for it, 39.7, that's our mean. Because if I don't have any predictors, my intercept is just the sample mean. Standard error of the mean. So that's how far off this intercept would be from the population intercept on average across samples. If I take 39 and some change and divide it by 4 and some change, that number is 8 and some change. A t of 8.74 would be observed less than 0.001% of the time. Now let me ask you, do I care about this? Do I care that my intercept is different than 0?
It depends on if we manipulated the data to make it 0.
Great answer. It depends on if we manipulated the data, but I haven't. So
So then it doesn't matter, right?
well, what this is telling me is that a mean of 39 and some change is different than 0, significantly. Meaning that people make money on average. The amount of money made is not 0. That's what this is telling me. Yes, exactly. Okay. Now, how could I turn that into something useful? Well, what if I had a prediction that the mean number of money made would be 50? Then I could subtract 50 from all of these, and then 50 would be my new 0, and this could be something interesting. But for now, it's not. Here's the confidence limits around my sample mean. And here's me trying to be nice. This is not SAS, this is me. I'm telling you that what this is beta 0. That's what this whole line refers to. That's what this is a solution for. Yeah. Here's one more model before we adjourn. Now I'm throwing in regular original education. So education is added after the equal sign. So y equals x here. And on Stata, y first, x second. So here's the model that's being fit by this code. ProcGLM automatically knows that you want an E. You don't have to tell it that. It automatically knows that you want a beta 0. Don't gotta tell it that. You gotta tell it what else you want. What I want right now is a slope for education. Right there. And same thing in Stata right there. And here's the solution that we decided was weird. Our intercept of negative 52 and our slope of 6.6. Because we didn't put centered education and we put original education. So negative 52 is the amount of money predicted if you have no education years. And that goes with this picture where the intercept is out there. And here's the code that I made to make the picture, by the way, in case you're curious. And our residual variance is down to 1594 from 1980 before, so that's a substantial improvement. All right. See, this ain't so bad. So things you would have to change to make this work for your data in a homework assignment, for instance. What data set? If you're in SAS. What outcome variable? What's your Y? So that's the first word after regressed or the first word after model. What's your predictor? Education, education. 3 things. See? Not so bad. Yeah. It's going to get cooler. And the good news is that we can use this same set of procedures for looking at all kinds of models. We can put in binary predictors, we can put in nominal predictors, we can put in nonlinear effects of quantitative variables, we can put in more than one predictor. We're going to do all of it with just this. Any questions before we adjourn? All right, then let me know if you need homework help. Please work on your next formative assessment and have good weekends. I'll see you all later.